Hi, everybody. Hopefully, the test went relatively well for you. And now we are ready to move on to unit number 5, which is probability. And this is your last lesson of the day. And we're just going to do a quick intro to probability. Now, normally in the classroom, we'll do some games, we'll work with dice. We can do a little bit more hands-on. Virtually, it's a little bit tougher, so we're not going to be able to do a lot of the hands-on things that we normally would get to do. But probability really isn't that bad, just involves perhaps a little bit more abstract thought. And you do probability in grade school as well. So our learning goals, we're going to introduce the concept of probability, and we're going to do some quick terminology, look at some probability experiments, and do some questions. So normally we'll start off with an activity. So when I say the activity was an experiment or an example of a probability experiment, which took a certain number of trials, very quickly on your own right now, you could find a coin and you could say flip it twice. And if you get heads come up twice, you win the game, we could say. So if you actually did that, grabbed a coin, flipped it twice, that was an example of a probability experiment. You got heads twice. I said you win. It took a certain number of trials, and you flip the coin twice. I could change that up by saying, keep flipping that coin until you get heads come up 3 times. Somebody could be really lucky and do 3 flips and have heads come up every single time. Somebody could be really unlucky and maybe it takes them 20 flips before they get 3 heads come up. You never know. But those are just probability experiments, certain number of trials, how many times you have to do something before you get the result that you want. So the outcome is that result. So getting 2 heads, getting doubles if we're talking about rolling a pair of dice. An event is the result from your outcome. So getting 3 points, getting 1 point, getting 0 points, let's say. Or like I just said in that little probability experiment, if I say you keep flipping that coin until you get 3 heads, and if you get 3 heads, you win the game, then the event would be you winning the game after you've got heads 3 times. As a very quick example. Our formula for experimental probability. Very simply, capital P, and I'm going to talk about what each one of these things stands for, equals the number of times event A occurred divided by the number of trials. Now, ACE is just the event. So it could be flipping heads, could be rolling a 1 on a die, could be what's the probability, if you talk about a spinner, of spinning a certain number for a game. So A is the event A. Now the one thing I want to draw your attention to is this, P of A. Do not forget when you are doing your solutions, say to the workbook questions, to your assignment, to your test, every single answer that asks you to find a probability has to start with a capital P and then in brackets whatever you're finding the probability of. So do not forget that, especially if you don't want to waste needless communication marks. So we're going to sit back and think about something, ponder the possibility. Is it possible to have zero probability? So think about that. Is it possible to have zero probability? Hopefully you are thinking yes. And if something has zero probability, it means it's not possible. Following from that then, what do you think all probability should have a value between? Hopefully you're thinking 0 and 1. So if you get a probability of 0, that means it's impossible. So right there, impossible. If you get a probability of 1, it's guaranteed to happen. So not possible, guaranteed. In the middle, where it says even chance, that would be a 50-50 shot, which would be 0.5. So the closer you get to 1, the more likely something is to occur. The closer you get to 0, the more unlikely it is. I'm going to warn you, there's going to be times on assessments coming up in the future where you are asked to give an example of something that's like impossible or 0, and give an example of something that's guaranteed or 1. You have to make sure that what you put for those are like legitimately impossible or legitimately guaranteed. For instance, if you want to say something that's impossible, if we look at a die, so we look at a dice, it only has the numbers 1 to 6 on it. Something that's impossible would be you saying it's impossible to roll a 7, or rolling a 7 on a normal 6-sided die is 0. That's true. There's no 7 on a 6-sided die. Don't say something like me making it to the NHL. Well, that's highly, highly, highly unlikely and almost impossible. It is not theoretically impossible. Some stroke of magic could happen, you could be the Zamboni driver and you play an NHL game. Who knows? So try to avoid saying those types of things. For guaranteed things, you might want to say something like, I only have black socks in my drawer. What's the probability that I randomly pull out a black sock? That would be 1. That's guaranteed. There's only black socks in there. Now, to give you a counterexample of kind of what not to do, and I know what you guys are thinking when you say these things, but don't say something like, it's guaranteed that I wake up in the morning. Well, it's highly, highly, highly likely, and it's kind of morbid to think about, it's technically not true. There might be a morning where someone doesn't wake up, so it's not guaranteed. Don't say, something that's guaranteed the sun's going to rise. Again, it happens every single day. It's not theoretically guaranteed. There's going to be a day when the sun burns out and it doesn't rise. Or some other stroke of crazy phenomena that might happen. So again, I know what you're thinking, but you want to give theoretically impossible and guaranteed scenarios. So again, you're going to see those types of questions pop up. Make sure that you give things that are legit and not just like highly unlikely or highly certain but not guaranteed. So our first example, 2 6-sided dice were rolled 20 times. Doubles were rolled 4 times. Determine the experimental probability of rolling doubles. You're going to express your answer as a fraction, decimal, and a percent. When you guys are looking at the workbook for this chapter, the first activity is you converting from fractions to decimals to percents. So you need to make sure for this unit, part of the curriculum expectations is you being able to convert between those three things. So we talked about probabilities. They're often expressed in one of those three ways, either fractions, percents, or decimals. To answer this question, again, we want good communication marks. Capital P for all of your answers for probabilities. In brackets, what you're finding the probability of. So we want to find the probability of rolling doubles. And our formula says count the number of times the event occurred, which it tells us it happened 4 times, over the number of trials, in this case, the number of times you rolled things, 20. Now we want that in lowest terms. Now I showed you guys how to use the ABC button on the calculators that I have in class. If you happen to have your own very similar scientific calculator, you could use the ABC button again. So you could type in 4 ABC 20, and it should give you 1 over 5. If you don't have to have that type of calculator, you're going to have to do things the hard way. Or if you go into D2L under content and then online stuff and take a look at the how to get a calculator emulator, I've posted a how-to video there. If you haven't already, you could download an emulator for a calculator that's kind of similar to the one that we used. And I think it has an ABC button. I'm not 100% sure, but I think it does. In any event, there's our fraction in lowest terms. To make that a decimal, 1 divided by 5, 0.2. How do you make something a percent? Multiply by 100. 20%. So there's our fraction, decimal, and percent of rolling doubles in this scenario. One B, write the probability of not rolling doubles as a fraction in lowest terms, again as a decimal and as a percent. So the key word here is not rolling doubles. So again, I'm going to do some thinking. We'll start off with our formula. Probability, not doubles. So let's think about this. I rolled doubles, I know from part A, I rolled doubles 4 times. How would I figure out then how many times I didn't roll doubles? Well, if you rolled doubles 4 times, that means every other time you didn't roll doubles. What's 20 minus 4? 16. So you didn't roll doubles 16 out of 20 times. Which, when you reduce that, is 4 to 5. Divide that to get the decimal, 0.8. Multiply by 100 to get the percent, 80%. Fraction, decimal, percent. And what you're going to notice is those all add up to 1. So if we look at, we got 4/5. On the example A, we got 1/5. What's 4/5 plus 1/5? 1. What's 0.8 plus 0.2? 1. What's 80% plus 20%? 100%. 1. Because rolling doubles and rolling not doubles makes up everything that's possible in terms of whether you're rolling doubles or not, makes up the entire sample space. Our next example, example 2. A coin was tossed 30 times. The experimental probability of turning up heads was 2/5. How many times did the coin turn up heads? So this is like working backwards. So there's a couple of different ways to do this. I'm going to show you both ways. So what we could do, some people might think this way. Start off with, we know that the probability was 2/5 of getting heads. If we make that a decimal, it's 0.4, multiplied by the number of times you flip the coin, we get 12. So again, the probability was 0.4. What's 0.4 of 30? 12. A different way to do this, or think about this, is setting up ratios and solving. So we know 2/5 equals something over 30, because we tossed the coin 30 times. So you got to ask yourself, what do you multiply 5 by to get to 30? And hopefully you're thinking that's 6. And whatever you do to the bottom, do to the top. What's 2 times 6? 12. Obviously, these are the exact same number. So how many times did the coin turn up heads? 12 times. How many times did the coin turn up tails? We flipped it 30 times. We just calculated we got heads 12 times. What's left over from, if we have 30 flips and we took 12 out, what's left? 18. Part C, what was the experimental probability of turning up tails? So capital P for probability. And if you're wondering why we didn't do that for A or B, it wasn't asking you for a probability, it was just asking you for how many times did something happen. So what was the experimental probability of turning up tails? So P of tails, we know it came up 18 times out of 30 flips. Now since I didn't tell you to do it as a fraction, a decimal, or a percent, you can do it however you want. Same goes for a test or assignment. If you do leave it as a fraction though, make sure that you reduce it. And if you made that a percent or a decimal, maybe go to a couple decimal places. Example 3, I'm giving you a bar graph. So a die was rolled, the results were recorded, 1, 2, 3, 4, 5, or 6. Those are the only options you can roll. How many times did each one of those numbers come up? So now we're getting information from a graphic. So looking at our graph, how many times was a 5 rolled? There's 5, it's at 2, so 2 times. Again, we weren't being asked for a probability, so we didn't have to put the capital P. For part B, find the experimental probability of rolling a 6 as a fraction, decimal, and percent. Probability of a 6. 6 came up twice. Now, out of. I don't know how many was out of. How many times did we roll the dice? Well, you're going to have to add up all the bars. So that was 2, that was 1, that was 3, that was 2. 2 plus 3 is 5, plus 5 is 10, 2 out of 10. Reduce that 1/5, 0.2, 20%. Find the probability of not rolling a 6. So capital P of not a 6. Now you could add up everything that's not a 6, or we kind of know that everything that's a 6 or not a 6 makes up the entire sample space. So if a 6 came up twice, everything that's not a 6 was 8 out of 10. And you would get that if you added up everything that's not the 6's. Reduce your fraction, 4 to 5, 0.8, multiply by 100, 80%. Now this next question leads us into a little bit more theoretical. So far we've been like doing something with a number of trials. So rolled this dice 10 times, flipped a coin 30 times. What would you normally expect? So this is a bit of a thinking question. What would you normally expect? Well, here's how you might want to think about this. How many sixes are there on a single die? There's just one. There's only 1 6 on a die. Out of how many possibilities? Well, how many different numbers are there on a die? 1, 2, 3, 4, 5, and 6. There's 6 different numbers. Only one of those is a 6, so I would normally expect 1 out of 6. Fractions don't have a lot of meaning to people. Percents often do. So if you make that a percent, divide and multiply by 100, you would get 16. So 1 divided by 6 times 100. Let's say round to 2 decimal places, 16.67%. So if we're comparing what we saw happen, say, in real life versus what you theoretically would expect, comparing these two things, we got pretty close, but we actually got a 6 happen 20%. So theoretically speaking, based off of what we witnessed, or based off the results I gave you, we actually beat the odds. We should have only got a 6 16.67% of the time, but we got one 20% of the time. Hopefully that makes sense. If we had a number that was lower than 16.67, then we would have done worse than the odds. We would have been unlucky. So that's it for experimental probability. To end off, I'm just going to start part 1 of theoretical probability. And what I'm going to go over here is a bunch of common probability tools, things we would have used in class as manipulatives, but also to make sure everyone's on the same page, because you're going to see these come up time and time again in questions. So a normal 2-sided coin. Everyone knows about these. There is only 2 outcomes. So your probability would be out of 2. What are those? Well, if it's a normal coin, heads or tails. Easy enough. A normal 6-sided die. I've already talked about that. There are 6 outcomes. So probabilities would be out of 6. And you could roll a 1, a 2, 3, 4, 5, or 6. And that's just if you just roll a single die. Things change when we involve more dice, or more coins for that matter. The next one, a normal deck of playing cards. There are a significant number of people that don't play cards, and so they don't know these. And decks of cards are used a lot for playing games and for analyzing probability. You have to know these things. You have to. It is an expectation of this course. You can't say, I don't play cards, therefore I don't know how to do this question. So we're going to go over all of the things you need to know. So I have 4 rows of cards there. Half are black, half are red. Some have numbers, some have A's on them. Some have letters on them. Some have faces on them. So let's start over here. Everything with an A is an ace. Then 2 to 10, self-explanatory. J for jack. Q for queen. K for king. Jokers are not included in a normal deck of cards. if you were to count all those. So here are some common characteristics. There are 52 cards in a standard deck. Again, we're not including jokers. There are 4 suits. These right here are clubs. These right here are spades. These are hearts. These are diamonds. Make sure you know that. There are 2 colors, black and red. How many cards are in each suit? There are 13 cards in each suit. So 13 cards per suit. Face cards. What's a face card? Face cards are cards that have faces on them. If we count all the cards that have faces on them, that's just Jack, Queens, and Kings. 3, 6, 9, 12. 12 face cards. Aces are not face cards. They don't have faces on them. If I was to give you a question that involved jokers, jokers would have faces on them. One would be black, one would be red. There'd be 54 cards, but we're just going to worry about a standard deck. And there's more than we can do with just those outcomes, but those are the ones I'm going to focus on. So again, make sure you know this or have this to refer to. The last thing would be a spinner. So the spinners don't really come in any standard number of sizes or number of pie slices. It's completely random according to the game you're playing. So here's a random spinner, and we'll just add a spinner in the middle. This spinner in particular has 8 regions. You could just count them. Has 4 colors. Purple, yellow, blue, and red. And it has numbers on them, but that doesn't really matter, because we can include that in the regions. So if we look at this fictitious spinner I gave you, what color is the most likely to happen? Blue. What color is the least likely to happen? Red. What about purple and yellow? They're even. They have a 2 out of 8 chance together. So that's just another thing you can use to analyze probability. Now I think this is where we were going to leave off. Tomorrow I will pick up from here and continue with theoretical probability. And if you've looked ahead, you're probably going to notice that I had written on there optional assignment in the announcement feed. I'm pretty sure that I'm going to give you an assignment, and I will be posting it on Thursday, and it'll be due Friday by 3 o'clock, just like your stats one was due on the same day as the test. So just look out for that. I'm going to try to make the assignment maybe a little bit more quote-unquote fun, since probability is typically a fun unit that we get to work with some stuff in a face-to-face setting. So I'll try my best, see if I can come up with something. But yeah, if you're looking ahead, I'm pretty sure the assignment's not going to be optional. It's going to be, you're going to have to submit it. And that's just better for those of you that want to bring your mark up. So that's it for our probability intro lesson. We'll talk to you guys tomorrow.